Hi everyone, welcome to the YouTube channel of P Division Official. I'm AMEY PUSEGAONKAR, and the topic for the video today is performing arithmetic and logical operations. Let's start with the PPT makers right now. So the PPT is made by VISHAL PUROHIT, SHLOK PUROHIT, AMEY PUSEGAONKAR, that is me, PUSHPINDER SINGH, and PUSHKAR KAMBLE. Let's start with the introduction. As you know, a computer works on instructions, and our system consists of machine instructions to perform some operations like addition, subtraction, multiplication, division, etc. Now, to achieve these operations, the system stores a data in registers. Now, to operate this data, the CPU has micro operations. So now, what is a micro operation? A micro operation is a simple operation performed on data stored in one or more registers. Start with logical operation. We transfer the data between the operation is a special symbol or a word that four types of micro operations. Phrases of information. Register micro operations, arithmetic micro operation, logic micro operation, and shift between the phrases is either true or false. Now, for this, the basic logic operations are AND, OR, NOT, NAND, NOR, XOR, and XNOR. Now let's start with the arithmetic operations. Arithmetic micro operations perform operations on the numeric data stored in the registers. Now the basic arithmetic micro operations are addition, subtraction, increment, decrement, ones complement, and twos complement. Now let's discuss these arithmetic micro operations one by one.
Further moving on to the addition operation. The addition arithmetic operation adds the value of two resistors and stores the output in the desired resistor. The symbolic notation for the addition arithmetic microoperations is R3 equals to R1 plus R2. Here R1 and R2 are the resistors whose contents we want to add. R3 is the desired resistor for storing the output. For example, 0 plus 0 is 0. 0 plus 1 gives us 1, and 1 plus 0 gives us 1. Here we have the different option. 1 plus 1 gives us 1 0, and here the 0 places the result and 1 is transferred as carry to the next column. The subtract arithmetic of micro operation subtracts the value of two resistors and stores the output in the desired resistor. The symbolic notation for the subtraction arithmetic micro operation is R3 equals to R1 minus R2. Here R1 and R2 are the resistors whose contents we want to subtract, and R3 is a desired resistor for storing the output. Here are the examples. 0 minus 0 gives us 0. 0 minus 1 gives us 1, because here 10 is borrowed from the next high order digit, which is equal to 2 in the decimals. So 2 minus 1 gives us 1. 1 minus 0 gives us 1. 1 minus 0 gives us 0 again. Increment operation. The increment arithmetic micro operation increments the value of resistor by 1. This means that this operation adds the value 1 of the given resistor and stores the output in the desired resistor. The symbolic notation for the increment arithmetic micro operation is R1 less than R1 plus 1. Here R1 is the resistor whose value we want to increment, and R1 is also the desired resistor for storing the output. For example, if we stores the value 1 in R1, after increment its value becomes 2. The decrement operation. The decrement arithmetic micro operation decreases the value of resistor by 1. This means that the operation subtracts the 1 from the value of the given resistor and stores the output in the desired resistor. The symbolic notation for the increment arithmetic micro operation is R1 equals to R1 minus 1. Here R1 is the resistor whose value we want to decrement, and R1 is also the desired resistor for storing the output. For example, if R1 value is 1, after the decrement operation, its value will become 0.
Ones complement. The ones complement arithmetic microoperation complements the content of a register. In this microoperation, 0 is converted to 1 and 1 is converted to 0. The symbolic notation for the ones complement arithmetic microoperation is R1 dash goes to R1. Here, R1 is the register whose value we want to complement, and R1 dash is also the desired register for storing the output. Two's complement. The two's complement arithmetic microoperations first complements the content of a given register and then add 1 to it. This microoperation is also known as negation. The symbolic notation for the two's complement arithmetic microoperation is R2 dash plus 1 goes to R2. Here, R2 is the register on whose value we want to perform 2's complement, and R2 is also the desired register for storing the output. Logical operations. Logical operation is a symbolic or a word that connects two or more phases of information. It is often used to test whether a certain relationship between the phases is true or false. Some of the fundamental logical operations are AND, OR, NOT, NAND, NOR, XOR.
So, my name is SHLOK Purohit. I am the group leader of this group. So, as discussed by Pushkar in the previous slide, there are various types of logical operators. The first one is AND. The AND logical operator returns true only if either of its inputs are true. In all other cases, the output we get is false. In computer programming, the AND operation is written as ampersand ampersand. So, the second logical operator is OR. The OR logic operation returns true if either of its inputs are true. If all inputs are false, the output is also false. In computer programming, the OR operation is usually written as two straight lines. The next type is NOT. As the name suggests, NOT, that is negative. The NOT logic operator returns true if the input is false, and the output is false when the input is true. In the computer programming, it is usually written as exclamation S. So that was all from my side. I would like to request Vishal to continue the further video.
Hello everyone, my name is Vishal and as Shlok said, I will continue further. So the next gate is NAND. The NAND logic operation, which stands for not and, returns true if its inputs are false and false if either of its inputs is true. NAND has the distinction of being one of two universal logic gates because any other logic operation can be created using only NAND gates. So the fifth gate is NOR. The NOR logic operation, which stands for not or, returns true if its inputs are false and false if its either of its input is true. NOR has the distinction of being one of the two universal logic gates because any other logic operation can be created using only NOR gates. So the sixth gate is XOR. The XOR logic operation, which stands for exclusive OR, returns true if either of its input differ and false if they are all the same. In other words, if its inputs are a combination of true and false, the output of XOR is true. If its inputs are all true or all false, the outputs of XOR is false. So the last is XNOR. The XNOR logic operation, which stands for exclusive not or, returns true if either of its input are the same and false if either of them differ. In other words, if its inputs are a combination of true and false, the output of XNOR is false. If its inputs are all true or all false, the output of XNOR is true.
So, thank you everyone. This is all from our side. Thank you for being so patient and listening to this video. I hope that all your doubts are cleared from it. So, don't forget to like and share this video. And if you like it, if you don't like it, please let us know in the comments. Bye bye, guys. Take care. See you in the next one.